Okay, so we are going to do the last of the 3 gas laws that then we will put together later, but the last of these 3. So here we go. This one deals with pressure and temperature. So before I get into those notes, I did want to just go ahead and put this FET of gas laws in here. The last law is called Gay-Lussac's law, and it deals with only temperature and pressure. So you should be able to kind of figure out what is going to happen. Remember, looking at this pressure gauge here, if I add particles, so I'm going to add some heavy particles and some light particles. It just means there are different sizes of gas particles. I'm going to keep the volume the same. Let's do half the size. So I'm going to keep it at this size. So look at the pressure now. It's 21.3. And all Gay-Lussac's law deals with is pressure and how it is affected by the change in temperature. So down here, you can add heat. So I'm going to heat this up. You can look at the little thermometer going up. I'm changing the temperature. It's getting hotter and hotter. And notice how the pressure gauge is rising. It was at 21. Now it's at 58. Keep heating it up. And as I keep heating it up, the pressure goes up and up. And look at the gas molecules. They are going faster and faster and faster. They're moving really, really fast until, look, it exploded. So basically the pressure got too much for this container and it exploded. That's why you really have to be careful with temperature and pressure, because if things get too hot or too cold, then it breaks the container. So I'm going to return the lid. I'm going to bring back up some more particles in here, okay? And it's still really hot in this container. But now let's watch the pressure as I lower, okay? So I'm going to make it colder. We're going to chill it down. It's getting way, way colder, and watch how the gas molecules slow down. So as molecules get slower, as they get colder, they get slower until they eventually get so slow that they actually come all together and turn into a liquid. That's a phase change from a gas to a liquid. But it's going to stay in the gas stage now, but you can see how they're moving way, way slower, and the pressure has dropped so much because we just got it colder, okay? So just kind of wanted to show you what this is really talking about. What this law is discussing is how temperature and pressure are affected by each other. So the pressure and temperature of gas are directly proportional, which means as temperature goes up, so does pressure, right? But it's the same as the law we talked about yesterday. They do the same thing. If pressure goes down, well, then that must mean that temperature went down. Those things would have to go hand in hand if the volume was kept the same. So as long as volume is kept the same, then temperature and pressure go up together, and pressure and temperature go down together. So how that formula is going to look is just how yesterday's looked, where we're going to have, which one do they like to write first? Let's see. Doesn't seem that much, but we're going to have P1 over T1 equals P2 over T2. And remember, the 1s and 2s just mean initial. So this is how the gas started, this initial pressure, this initial temperature, and this is how it ends, final, the final pressure and the final temperature. Okay? That's all we really need. We're going to use that formula to solve this last problem. So this was Boyle's Charles. Now this one should be, I'm going to get higher and rewrite the formula above it. So this one right here is going to be for Gay-Lussac's law. Okay, so I'm going to rewrite our formula. I'm writing it above the question just because of space. So it belongs to the one right here, the one I'm working on. So P1 over T1 is equal to P2 over T2. Okay. So now we're just going to read the problem. We're going to identify our variables and plug them in. So a gas left in a used aerosol can is at a pressure of 125 atm, okay, and at a room temperature of 27 degrees Celsius. So this is my P1, because atm is a pressure unit, and Celsius is a temperature. That's my P1, T1. Starts at that pressure, starts at that temperature. if this can is thrown into a fire, what is the internal, get this to go up, there we go. The internal pressure when the temperature reaches 927 degrees Celsius. So this will be my T2, my final temperature. So we have P1 and T1 and T2. What we're missing is P2. That's what we're looking for. What will be the final pressure? That's the one we're missing. You're always going to have 3 and be missing 1 and have to solve for it. Now, the problem with any of these that start with temperature is all of our mathematical equations need us to have the temperature unit of Kelvin, not Celsius or Fahrenheit. But everyone measures stuff, like in real life, we use Celsius thermometers or Fahrenheit thermometers. We don't really use Kelvin that often, so we have to convert it anytime we need to do these kind of math formulas. So I'm going to convert my 2 temperatures into Kelvin first. So that's always your Celsius. So like remember, it was Celsius plus 273 equals it in Kelvin. So I'm going to take 27 degrees Celsius. I'm going to add 273, and that's going to be my temperature in Kelvin for my T1. I don't know why I put TI. I meant T1. Okay, and then I'm going to have my 927 degrees Celsius. That's very hot. Thrown into the fire, plus 273, and that'll be my T2 in Kelvin. All right, so let's add those up and figure it out. So 27 plus 273 is 300. Should have been able to do that one in my head. 927 plus 273 is 1200. Okay, so those are my new Kelvin values that I'm going to actually use in my formula. I can't use them as they were given to me in Celsius. So now I'm ready to set this problem up. So my P1 is on top, and they gave me that. It's 1.25 ATM. And it's over my T1, which we solved for over here, is 300 degrees Kelvin. And that is equal to my P2, which I don't have. This is my missing variable. There we go. So that's my missing variable, and it's over T2, which we solved for over here, which is 1200 K. All right, to solve for P2, we're going to do the same thing that we did yesterday, where we do cross multiplication. So cross multiplication says things that are crossed from each other, like these, I'm going to multiply, and then I'm going to divide. Oh, I can't make that divide sign up higher by the number that's left over. So how that will basically look, I'm going to write it down here. Let's pretend I'm writing it in the right spot. I don't know why I keep not adding more space. So I have 1.25 times, well, let's write the units. Let's be good little scientists here. So 1.25 ATM times 1200 K is going to be divided by what was left over, which was this 300 degrees Kelvin, or 300 K. Now notice how the units are going to cancel. So K and K are on top of each other. So they're gone. And it's going to leave me with the ATM unit, which is a pressure unit, which is what they asked me for. We're solving for P2, which is a pressure unit. So that should work out. So I know it's set up correctly because the right units cancel. And now I just put it in the calculator. I have 1.25 times 1200 equals, and then I divide by the bottom, which is 300. Divide by 300. And I get the answer to be 5 on the dot, actually no decimals, ATM. And that's the answer for P2, which is what we just solved for. The pressure at the end would be 5 atmospheres, which is actually a really high pressure. Normal pressure, like just our regular air pressure, is usually 1 ATM. All right, there we go. Done with notes for today.